Hello, hello. It is now 3 days after I recorded the solutions to this air gap problem. And I looked at my notes, and my notes mention that the magnetic field in the iron and in the air gap is 0.91 Tesla. Yet, in my solution, I write 0.81. I'm sorry, it happens that it's a slip of the pen. Of course, it is 0.91. If you put in all the numbers that you know, you will confirm that it is 0.91. With my apologies, but I'm glad I caught this way before I am going to post the solutions. Bye. Hello, 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 hello. Today I'm going to discuss with you the solutions to the problem where we have an electromagnet with a very small air gap. Here is solid steel. It's a cross-sectional area about 5 square centimeters. The relative permeability is about 2500. The radius of this steel is roughly 8 centimeters. There are windings here around the steel, and windings, 130 windings, and we draw a current of 15 amperes through these wires. And here is an air gap, about 2.5 millimeters. I mentioned to you that because this air gap is so much smaller than this diameter, that you can assume that there are no fringe fields. So there are no fringe fields here at the air gap. So that means that the magnetic field inside the steel will be the same as in the air gap. So I could have asked you, what is the magnetic field inside the steel? Same question. So we want the magnetic field strength in Tesla. Clearly, we're going to use Ampere's law, since we have a nice case here of symmetry. Let's go over Ampere's law first. Choose any closed loop. Any. Doesn't have to be a perfect circle, it could be crooked, but it has to be a closed loop. Attach to that closed loop an open circuit. Open surface. I said an open surface. In some cases, you may prefer to choose a flat surface if that's possible. But it doesn't have to be a flat surface. But it must be open. And the opening is where you attach the surface to that loop. That's where it's open. So, if this is a wire through which a current runs, I, and I choose a closed loop, and I attach to that closed loop an open surface. And in this case, the open surface will be a flat surface through that circular path that I have chosen. Ampere's law will now say that if I go around this path, this closed loop, that the integral along that closed loop, B dot dl, B is the vector B along the closed loop, and dl are the vectors of the small displacements dl as I go around. It's a dot product. Since it's a dot product, the answer is a scalar. And this closed loop integral is the magnetic relative permeability times the permeability of free space times the current that penetrates through that open surface. I stress the words penetrate because many books call this enclosed. And enclosed is nonsense because it's ill-defined. So they will argue then in this case that this circle encloses the current. Very ill-defined. Do your math and you will see it's ill-defined. Unique is if you attach an open surface to this closed loop. Unique is that the current pokes through that surface. In this case, if it is a flat surface, it's clear that it pokes through here. Now, if you have a current wire that goes like this and then returns, if now you take a closed loop and you take a flat surface, open surface, and the current penetrates this way and then later this way, then I penetrate is 0. Keep that in mind. Okay, so this is the equation that we're going to use later to solve this problem. Clearly, in this particular case of a current wire, only if you choose a concentric circular closed loop will you be able to calculate the B field. For any other loop that you choose, any other shape, this is still correct, but you won't get the value for B if that's what you want to get. So you often, or I would say, you will only succeed using Ampere's law if there's a clean-cut example of symmetry, which we have in our problem. If you have a current going through wires which themselves are a loop, like this, then you can calculate the magnetic field at all locations, although maybe mathematically a pain in the neck, using Biot-Savart. I will not discuss Biot-Savart now, but I just want to mention that the magnetic field inside this loop is way stronger than outside, and of course it is the strongest at the center. If now we have a solenoid with many windings, and a current I going through the wires, then using Biot-Savart you can calculate the magnetic field inside the solenoid, and you will then conclude that the magnetic field outside that solenoid is much smaller than inside. Of course, that depends on how many windings you have, and it depends also on the strength of the current. So it depends on geometry. But in general, the magnetic field here will be way stronger than there. Now, if you place inside the solenoid ferromagnetic material, well, then the magnetic field strength will be enormously enhanced, because the magnetic domains of the ferromagnetic material will start to co-align. They will make an attempt to co-align with the external magnetic field. And I call the external magnetic field then the field that is produced by the current through the wires. So with ferromagnetic material, this was ferromagnetic material, the magnetic field inside the solenoid where the ferromagnetic material is so much higher than outside, where there is no ferromagnetic material, that you can completely ignore, in general, the magnetic field outside the solenoid, which I call now an electromagnet. And that's what we have here. Here we have the steel, which is the ferromagnetic material. Here are the windings. So if the windings were clockwise as seen from below, magnetic field inside the solenoid would be in this direction. And the magnetic field would be enormously enhanced by this factor 2500. That factoring. The magnetic field would go all the way around. Everywhere in this ferromagnetic material, the field would be the same, negligible outside. And since there is no fringe field here, the magnetic field inside the gap would be the same as inside the steel. So, the problem is quite symmetric. So we're dealing with circles. Here I have the same picture that I have on the left. And I have here chosen my closed loop. My closed loop is chosen inside the steel, but also, of course, here, through the gap. Now, you have to choose a surface, an open surface attached to that closed loop. Well, you might as well make it simple, but you can choose any surface as long as it's open and as long as it's attached to the loop. So this is my red closed loop. So you might as well choose the flat surface inside this circle. You will see then that that flat surface is penetrated n times right here by the current I. And so I penetrate is n times I. So now we're well on our way, since I have chosen a circle, and we have chosen axial symmetry, of course. Clearly B has to be the same everywhere here, for reasons of the symmetry. So, we're almost done. So here I have rewritten Ampere's law in a somewhat different way. Brought the Km out here. The magnetic permeability of free space, μ0, you have to look that up, so many henries per meter, SI units. Now if you go around here, you have to go all the way around. The routing through the steel is about half a meter. And the routing through the gap is only 2.5 millimeters. But the steel has kappa m of 2500, the gap does not. So when you make this closed loop integral, you have to separate out the part that goes through the steel and the part that goes through the gap. And so only this one has the kappa m and this does not have the kappa m. The length of this path without the gap is 2 pi r minus d, if d is the opening of the gap. But d is so much smaller than 2 pi r, it's about 200 times smaller, that you can also assume, approximation, that 2 pi r minus d is 2 pi r. If you want to take the d into account, be my guest. But this is a very good approximation already. With that approximation, you will immediately find what b is. So here is the term due to the steel, and here is the term due to the gap, the air gap. You know all these values, you know I, n, mu 0, you know kappa m, and you know d, and you will find 0.81 Tesla. To remind you, 1 Tesla is 10 to the 4 Gauss, and the magnetic field at the surface of the Earth is roughly 1 Gauss. Now comes something very interesting. Your first instinct when I posted the problem may have been, well, what the heck, just a gap of 2.5 millimeters probably will have almost no effect. But that's not true. It has a huge effect. And the reason why it has a huge effect, that 2 pi r over kappa m is 2 times 10 to the minus 4, but d is 2.5 times 10 to the minus 3. So d is roughly 10 times larger than this term. So because of this small air gap, the magnetic field in the steel and in the air gap is 10 times lower roughly than if there had not been an air gap, and that is not so intuitive. So yes, the path through the steel is about 200 times larger than the path through the gap. But in this path, which is 200 times larger, kappa m is 2500. And so the winner is really d, if you want to call that the winner. And what I mean by that is that the effect of the air gap, very small, is huge. It lowers the magnetic field by roughly a factor of 10. Well, I hope you have learned some physics. More important for me than anything else is that you understand Ampere's law. Use any closed loop that you want to choose, anyone, no matter how crooked, as long as it's a closed loop. Attach to that closed loop an open surface. And then Ampere's law will tell you what the integral is of B dot dl along your closed loop. It's related to the current that penetrates through your surface. And the idea that it encloses a current, no, I don't like that. I don't like the idea of enclosing because it's ill-defined. But penetration of a surface is uniquely defined. Okay? Yes, I hope you've learned some physics. It is a first year college problem. This was part of my electro E&M course at MIT for freshmen. But it's a cute problem because it is not so intuitive how immensely strong the effect is of such a teeny little air gap. Alright, I hope that there will be at least 30% correct answers when I record this is often months before I post it. So I have no idea how well you will be doing, but I hope that there will be 30% or maybe even more correct answers. Have a nice day, take care, and of course it's a given that we will be friends. I would like that, and I hope you like that too. Hello, hello, hello. I would like to add a few more things that I didn't discuss in the solutions because they were irrelevant for the solution. But it is something that many of you are often confused about. Sorry for my outfit, I just came out of the shower. So the question now is, what is the direction of the magnetic field? It depends on how you wind the wires and in which direction the current goes. Take a look. So this is a vertical rod. Think of this as being a vertical rod. If I wind the wires as seen from below around this rod in a clockwise direction, and if then the current enters here and comes out here, the magnetic field is in this direction. However, with the same winding, if the current is in the opposite direction, the magnetic field is down. There is another way you can wind the wires around the vertical rod, looking from below in a counterclockwise direction. If then the current comes in here and it comes out there, then the magnetic field is in this direction. Therefore, if you reverse the current, then it comes in here and comes out here, the B field would be in that direction. The reason why I stress this, even though it's irrelevant for our problem, because I didn't ask you what the direction was of the B field, I only asked you what the magnitude was. The reason why I stress this is that there are many books who state that if the wires are wrapped around in clockwise direction, that then the B field is up. That is not necessarily true, because it depends on the direction of the current. I hope that is clear now. So if you ever see in your books a clockwise winding and they say the B field is up, they have then assumed that the current goes from below, goes in below and gets out above. So let's suppose that I had asked you in what direction the B field was here. If you look from below, the winding here is counterclockwise, just like this. So that means if the current was flowing in here, we would have the situation that the B field is down. The B field, the current would come out here, would go in here and come out here. And so right here in this part, the current would be going to the left. And right here it would be going to the left. And that's also the case here. To the left, to the left, to the left. So, if the currents were going in here and out there, magnetic field would be down. If the current would go in here and out there, magnetic field would have been up. Okay? I hope that you become critical when you read books. I had once an argument with a viewer who said that whenever the winding is clockwise, the B field is always up. That is not true. It can be up, but it doesn't have to be. Alright, take care. Over and out. Over and out. Maybe that sounds better. Hello, hello. It is now 3 days after I recorded the solutions to this air gap problem. And I looked at my notes, and my notes mention that the magnetic field in the iron and in the air gap is 0.91 Tesla. Yet, in my solution I write 0.81. I'm sorry, it happens that it's a slip of the pen. Of course, it is 0.91. If you put in all the numbers that you know, you will confirm that it is 0.91. With my apologies, but I'm glad I caught this way before I am going to post the solutions. Bye.